This video covers section 5.2, which is titled Infinite Series. We saw in the last section what a sequence was. A sequence, remember, was just an ordered set of terms, and we explored the idea of an infinite sequence, which is an ordered set of an infinite number of terms. Well, all a series is what you get when you add up all those terms from an infinite sequence. So we're going to explore that, and towards the end of the section, in the next video, we'll take a look at what a geometric series is, which is a specific type of series that we commonly see and use. So let's go ahead and introduce this section. We're going to start with the idea of taking partial sums, and we're going to take a look at a specific sequence. So suppose we take a paper that is 1 foot by 1 foot, and let the sequence a sub n be the area that results when we fold that paper in half n times. So the very first term we get is when we fold it in half 1 time. So you fold it in half, that piece of paper is now 1/2 by 1, so it has an area of 1/2. And if you were to do that with a piece of paper, what you would end up seeing is every time you fold it in half, its area changes by a factor of 1/2. So the next area, when you fold it again, is going to be 1/4. And when you fold it again, you get 1/8. Fold it again, you get an area of 1/16. That piece of paper is getting smaller and smaller and smaller. The area is getting smaller and smaller, and so on. So now we're going to define what's called a partial sum. And the way we find a partial sum is by adding up the first n terms out of a sequence. So the first partial sum would be what we call S1, which is basically the sum of the first term, which isn't really a sum, it's just the first value. So S1 is 1/2. Now S2 is what you get when you add the first term with the second term. So you're adding up the first two terms, which in this case is going to be 1/2 plus 1/4, which is 3/4. And then likewise, S3 is what you get when you add A1, A2, and A3. We know that the first two terms add up to 3/4. If we add 1/8 to that, you get, what's that? 6/8 and 1/8, you get 7/8. And then you can continue on. The first four terms are added, you get the fourth partial sum. And in this case, it's going to be 7/8 plus 1/16. It's going to be 15/16. So, can you make a conjecture about this limit right here? What do you think the limit is going to be as n approaches infinity of the partial sums, the nth partial sum? So what does it look like these partial sums are approaching? What value are they getting closer and closer to? And if I'm looking at it, it looks like they are approaching 1, right? So let's take now a look at this definition. So we already said an infinite series is an expression of the form given. So basically, you're just adding up the terms of an infinite sequence. Okay, so then what we call the partial sum is given by this. That's what we just did up above. Like when we found the fourth partial sum, we added up the first four terms. And then what we can get is a sequence that is formed by those partial sums. So, in other words, if you were to take the partial sums in this example above, they would form a sequence where the first partial sum is 1/2, the next one is 3/4, the next one is 7/8, the next one is 15/16, and so on. This is a sequence. This is a sequence of the partial sums. Okay? Now, what does it say? if the sequence, right here, if the sequence of the partial sums converges to a real number s, then the infinite series converges. If we can describe the convergence of s, we call s the sum of the series, and we write that the sum of that series is equal to s, and in that case we say that, again, it converges. If it doesn't, if those infinite number of terms, if the infinite number of terms right here does not add up to some, does not converge towards some finite value, if it just keeps getting larger and larger and larger, then we say it diverges. So basically, again, what we're saying is, I'm going to recap this. An infinite series is the sum of an infinite sequence. It's what you get when you add an infinite number of terms together. Now, it may seem unlikely that we actually get something like that to add up to something, but that's precisely what does happen sometimes, because eventually what happens is you keep adding terms to this sum, eventually you're adding terms that are so small that you're not really adding anything anymore. So the sum is actually converging towards a value. And what most of the rest of this chapter is going to be spent doing is figuring out how to tell if a series converges or diverges. So let's take a look at another example. Example 1 says, for the series 1 over n times n plus 1, use the sequence of partial sums to determine whether the series converges or diverges. How do we know it's a series? Well, it's a sum, right? It's a sum of an infinite number of terms. And so let's write out the terms of this sequence first. So what is a sub n, starting with the first term? Should be 1/2. Next one should be 1/6. Then we have 1/12 and 1/20. And so those are the terms of the sequence, which means the series looks like this form. So when we are talking about the series, remember that's just the sum of those terms. So 1 over n times n plus 1 is the sum of 1/2 plus 1/6 plus 1/12 plus 1/20 plus ... And the question is, does that actually add up to something? We can see that it is, that those numbers are, the terms in this series are tending towards 0, which means eventually we should be adding basically next to nothing. As we said in the definition on the previous page, a series converges if the sequence of partial sums converges. So in other words, are those partial sums tending towards some value? And so let's write those out. S1 is just the first term. S2 is the sum of the first two terms. So that's 2/3. And we have S3 is 2/3 plus 1/12. That's going to be what, 8/12 plus 1/12 is 9/12. So it's going to be 3/4. Let's do one more. Fourth partial sum is going to be 3/4 plus 1/20. 3/4 is 15/20 plus 1/20 is 16/20. 16/20 is 4/5. All right, so let's look at the sequence of those partial sums from 1 to infinity. So it looks like that first partial sum is 1/2, and then we get 2/3, 3/4, 4/5, and so on. Well, can we come up with a formula for that? Let's take a look at that first. So it actually looks like it's a pretty easy formula. It looks like, because remember that first term is n equals 1, the next term is n equals 2, and so on. So when you look at that, it looks like the first term, or the numerator, just follows n. So we have n on the top, and then the bottoms are just one bigger than that. So that's n plus 1. Well, since we could come up with a formula, then based on what we learned in the last section, in section 5.1, we can tell if that sequence converges or diverges, right? What do? We just take the limit. We take the limit as n approaches infinity of n over n plus 1, which is infinity over infinity. But if we apply L'Hopital's, we can see that this is the limit as n approaches infinity of 1 over 1, which is 1. So it looks like that sequence of partial sums is approaching 1. And if we're just looking at all these partial sums, you can see that those are getting bigger. They are getting closer and closer to 1. So what can we say? We can say, so because the sequence of partial sums converges, that means, it said this in the definition here, if the sequence of partial sums converges to a real number s, then the infinite series converges. So notice the sequence of partial sums converged towards the value 1. It approached that limit, approached 1. So our series from n equals 1 to infinity, this is an infinite series, 1 over n times n plus 1, also converges. In other words, this infinite sum that we talked about right here, if you add up the infinite number of terms there, they all add up to 1 because those partial sums are approaching 1. So hopefully that makes sense. That's kind of the idea of the way a series works and whether or not it converges or diverges. In the next video, we're going to take a look at the geometric series. All right, see you in the next video. Thank you.